Swayam Prabha. Digital India. Educated India.
Lecture on regulation of enzyme activity through inhibition. In the previous lectures, we talked about different kinds of inhibition: competitive, uncompetitive, non-competitive, substrate, and so on. And we also discussed why we need inhibition, which is to regulate the amount of enzyme that is produced so that other biochemical pathways are not disturbed, so that the energy required for the product formation is minimized, and all these concepts. So we went into great detail and tried to understand competitive inhibition, and then we started working on uncompetitive inhibition, and which is what we will do today. We started on it in the last class but didn't get the time to finish, so we'll get back and try and remember the concept of uncompetitive inhibition. So if you look at on your screen, what we had in competitive inhibition was that the substrate and the substrate and the inhibitor, they were competing for the active sites of the enzyme. Whereas in uncompetitive inhibition, that's not like that. The reason is that in the uncompetitive inhibition, the inhibitor does not go and sit on the active site of the enzyme, but in some other site, right? So that is what happens. If you see in the picture here, the active site is given by this semicircle, whereas the slot for the inhibitor, the other slide, is a square. So the inhibitor goes and fits into this slot, and the substrate goes and fits in the other slot. So as a result, at one point of time, you can have two options. One is the substrate combining with the enzyme to form the complex which is needed for the product formation P, and the other possibility is both the substrate and the inhibitor combining with the enzyme to form this complex ESI, which is not required for us. As a result, this will not lead to product formation, right? So if you go back to your notes, you will see that we started working on it. So what are my assumptions for the process for the system? There are what are they going to be? One is that if you look at the two reactions, one is that reaction 2 attains equilibrium. The second one is that this species over here attains quasi steady state, and the third one would be the constraint equation. So at any point of time when I give you this system, and if I give you a lot more complicated system, right, it doesn't have to be just competitive or uncompetitive inhibition, it could be a combination of different kinds of inhibition. So if I at any point of time in an assignment or the test give you problems where these different kinds of inhibitions are sort of combined, so what would be your thumb rules? One, you have to figure out three things you have to figure out quickly. One is which are the reactions that attain equilibrium, right? So figure that out, A, first. Second is which are the species that attain quasi steady state. And third, what would be the third step? Apart from the constraint. The constraint is there, but that apart, what else do you need to figure out? Right. Which is the rate limiting step or the slowest step, because the rate of product formation is going to be dictated or governed by that particular state. So any combination I give you, these are some examples we are doing which are prototypes, but if we go beyond these prototypes and come up with more complicated things, what you have to figure out is what are the reactions that attain equilibrium, A, what are the species that attain quasi steady state, and C, which is the reaction that is a rate limiting step which will govern the rate of product formation. And finally D, you have to figure out that what is the constraint equation. So what are the elements that are present in the constraint equation, which is to figure out that in what form the enzyme is present. So what are the different complex forms? In this case, as you look at the screen, you will see the enzyme is present as ES, as ESI, and also as E, which is a free enzyme. So your constraint equation is going to be that. So if we go here, so this is the reaction, the equilibrium for reaction 2, right? You see on the screen. So which is ESI gives CES times CI over KI, KI being the equilibrium constant, the backward over the forward rate constant. So next, right. Next is the constraint equation, which I already discussed, the Ce plus Ces plus Cesi, that is the enzyme in 2 complex forms plus 1 free form together equals the total amount of enzyme that you put into the system at the start. And the last one is the quasi steady state. One of the things I pointed out in the last class, if you remember, what is the major difference between this quasi steady state and the quasi steady state we wrote for competitive? It is that we have 2 extra terms. It is so that it turns out that those 2 extra terms cancel each other because you make a equilibrium assumption for reaction 2. But you should be careful enough to write those terms, because there could be cases where those terms don't necessarily cancel out the way it does over here. So that is one another thing I'm trying to point out, because see, what we are trying to figure out through these examples that we are doing, what would be a strategy or a mechanism to solve a problem of enzyme inhibition in cases where there are different kinds of inhibitions that are involved. The reason is the biochemical pathways that are there in the body are much more complicated than the simple prototypes of simple competitive, non-competitive, uncompetitive that we are doing. So that is the reason. And what I want you to be able to figure out through what we are doing is that, given a system, if at any point of time in your research you are working on a system which has these multiple enzyme pathways and multiple inhibitors inhibiting or regulating those enzyme activities, how to come up and be able to solve. So we are taking things one step at a time, doing the simple cases, but in real life, when you do, there could be a combination of these different kinds of inhibition in the network of reactions. So typically in the human body, biological network, biochemical pathways, these are networks of reactions which are series and parallel. They cut across, intersect with each other, and they're parallel to each other, and then there are complex inhibitors that are there, and there could be inhibitors which inhibit more than one reaction simultaneously. So what is needed is to be able to bring those ideas together, and we are trying to come up with a strategy of a formal theoretical framework for that. So that these are the steps in that theoretical framework. And so if you do that, you will find that your CES, so first here CESI has been broken up into CES and CEI. Okay, now CES is broken up into CE times CS over Km. So that you can substitute over here, and then you will get the CES as a product of the three components. Fine. So I think this is probably where we are, right? In the last class, did we stop here? Somewhere around here we stopped. Yeah. So if you look over here, what is happening is that the CE is now expressed in terms of CE naught, and as I said before, the reason we do that is because it's not possible to measure the free enzyme, right? So CE now is given by CE naught over a denominator which is composed of the substrate as well as the inhibitor, right? Fine, is it clear? So in the absence of the inhibitor, this would go back to the simple model, no inhibitor model. So CES now, CES, which is written as CE times CS over Km, now could be written as CE naught over CS over Km plus CS1 plus Ci over Ki. I'll give you a few seconds to write this down if you want to. So what is the rate going to be? Simply K2 times CES, because the rate limiting step is the product formation step. Okay. So what we'll do is we'll simply compute the rate here, which is dCp. The product formation rate is dCp dt equals K2 CES, K2 times CES. Now that can be expressed as in terms of CE naught and CES. So what we find over here, if you look, is that again we have been able to revert back to the Michaelis-Menten form. Okay, that is what we find. Look at the rate equation up there on the screen. Okay, so you will see that we have been able to revert back to the Michaelis-Menten form. So what is the difference? If I ask you, those who were here for the competitive inhibition, what is the difference between the rate we find over here and the rate we had in competitive inhibition? Yeah, maximum rate has increased, and what else has increased? Both the slope and the other asymptote, both of them have increased, right? So your Km hat has also changed. Sorry, your Km hat has changed and the maximum rate has changed, right? So now your Km hat is this number, okay, given over here, and your Rmax is the numerator over here. So you might just want to write down these two, the Km hat and the Rmax, for the new system, which are Km hat and Rmax hat actually. So if you look at these two, once you've written, I'll ask you a quick question on this. Okay, so once you've written this Km hat and Rmax hat, can you make some comment on this? Is there something that you think is worth saying? Both have changed, fine, but what else? Just look at them a little carefully. Both Km hat and Rmax hat have changed, but what is interesting about them? Not so complicated. Just look at these two quickly and tell me these two numbers. What? So as compared to, say, without inhibition, I'm giving you a hint here. In the absence of inhibition and in the presence of inhibition, so both Km hat, so Km hat has decreased, huh? Or in other words, the ratio remains the same, right? So that is one of the things you notice. So this is one of the differences between this and competitive inhibition. In competitive inhibition, one of them changes, but the ratio also changes. In this case, both of them change by the same factor, as a result of which the ratio remains the same. Why is that important? We'll see in the plot, and you can kind of sort of guess also, right? So this is it, and so this is your K hat and Rmax hat, and since your Ci and Ki are both equal to greater than 0, which means that your Km hat and Rmax hat are both lowered now as compared to in the absence of inhibition. Okay, which makes sense, because if you add inhibition not to increase it but to decrease the maximum rate. And however, this is what I wanted to point out, and now it's on the screen, is that the ratio remains the same. As a result, the slope in the plot remains the same. So maximum reaction rate decreases, but the slope in the curve remains the same, and I will show you a picture of that in a while. Okay, so this is on uncompetitive inhibition. We'll now go to non-competitive inhibition, but if there is any quick question on uncompetitive inhibition, you can ask me right now. Right? No question? Okay. So uncompetitive inhibition is, sorry, non-competitive inhibition is essentially this, what a little bit is written on the screen. So what happens is that both the active sites and the non-active sites are blocked by the inhibitor. Okay, both the active sites and the non-active sites are blocked by the inhibitor. So this is the most potent form of inhibition, so to say, right? If you're talking of different forms, so this is a form where both the active site and the non-active sites are blocked by the inhibitor. So if you want to inhibit as much as possible, then probably this is a mechanism that you'd go for. Now I'd like to ask you, in terms of reaction, because we've done 3 different kinds before: without inhibition, competitive, and uncompetitive. What do you think would be the reaction mechanism? Not in detail, but just give me a sense. What do you think would be the reaction mechanism for this? Which two? Uncompetitive and competitive. Very good. That's the answer. So it's a combination of those two. So it's now on your screen. So as you see that this is see the yellow thing and the red dots over here. So the red is the substrate, the blue is the inhibitor. Okay. So this is where you can have the inhibitor blocking the non-active site. This is the inhibitor blocking the this is the substrate taking up the active site, but there is a possibility that the inhibitor might also block the active site. So the reaction scheme, as you see, is a combination, as just as I said, of the last two. So in the competitive inhibition, you had equations 1 and 2, right? So which was the equation 1 is the general equation in the absence of inhibitor, which is the substrate and the enzyme reacting to form the complex, that forming the product. Equation 2 was for competitive inhibition, where the inhibitor was competing with the substrate for the attention of the enzyme, for the attention of the active sites of the enzyme rather, and these two form the competitive inhibition. And 1 and 3 formed the uncompetitive inhibition, where the enzyme was not directly binding to the active site of the the inhibitor was not directly binding to the active site of the enzyme, but it was binding to the non-active site, to the complex, so to say. So here, as I said, this is the most potent form of inhibition, and here what happens is that all three together, all three reactions together happen, which is the first reaction, the normal reaction, the first kind of inhibition, that is the competitive inhibition, and the uncompetitive inhibition. All three together happen. Okay, it's strange kind of why this name comes, the non-competitive, but it is competitive in a way. So yeah, so I'll give you a few seconds to write down the reactions if you want. Okay, so there's a slight error here, and I need to point that out. These k's that you see here, the forward and the backward rate constants all through, are going to be little k's, small k's, not the big k's, because big k's are for equilibrium constants and small k's are used for reaction rate constants. So please make that small change. Yeah, in all the reactions 1, 2, and 3, the k's are going to be small k's. Okay. Now, so we talked about strategy. So what our strategy is going to be in terms of, you know, the framework for deriving what we want to. What is the first thing we should consider? What are the reactions that attain equilibrium? So what are the reactions that attain equilibrium here? What do we assume? These are assumptions essentially. We're not sure if they attain equilibrium or not. No, just EI and ESI. Okay. These two we assume that attain equilibrium, just EI and ESI, and ES, that reaction does not attain equilibrium, it attains quasi-steady state, because you have to figure out why can it not attain equilibrium. Yeah, answer, tell me this, why do you think it shouldn't attain equilibrium? Because if it attains equilibrium, then what will happen? And how will product be formed, you know? So it will be just engaged in the backward and the forward reaction, right? But if for product to be formed, it's not possible for that to attain equilibrium. What it attains is a quasi-steady state. So as I said, that what we do first, we figure out what are the reactions that attain equilibrium, A, my first goal. So that the answer to that is reactions 2 and 3 attain equilibrium. My second question that I ask myself is, what are the species that attain quasi-steady state? The answer here is only one species, which is ES. Okay. My third question is, what is the rate limiting step? The rate limiting step here again is the formation of ES to E and P, right? And as you know that, you know, reactions that attain equilibrium are much faster anyway. And the last one would be that what is the constraint equation? So what is would be the constraint equation here? How many species it should involve? For the first time, it will involve 4 species, which are the free enzyme E, then the complex 1 ES, complex 2 EI, and complex 3 ESI, right? So what I want you to do is, I have the things here, but I want you to quickly go and write some of them. So first one is that reactions 2 and 3 attain equilibrium. So this is what you have, and if you want, you can make a note. So CEI is given as CE times CI over KEI. That's first. Second is ESI, sorry, is given as CES times CI over KEI. Okay. But our goal is to be able to express these complexes in terms of the elements, right? In terms of the respective elements. So again, as I said, there is a slight typographical error here. These k's are going to be small. I mean, well, even with big k's, it makes sense as long as you're consistent. But the nomenclature, the standard nomenclature, is that small k's for reaction rate constants. So we'll stick to that. So equation 5, as you see in equation 4, we have been able to already accomplish what we wanted, which is express CEIs in terms of CE and CI. Now in equation 5, we still want to express CES in terms of the CE and CS. How do we do that? By using the quasi steady state for CS, right? So if we do a quasi steady state for CES, what will you get? How many terms will you get for quasi steady state for CES? When you write the quasi steady state equation, so ddt of CES, how many terms? 5 terms, right? You get 5 terms. Is it clear to everybody? You get 5 terms, 2 of which will cancel out because of the equilibrium assumption given by equation 5, right? So as you see on the screen now, so you have 5 terms. ddt of CES has 5 terms, 3 from the first reaction 1, 2 from reaction 3, and the 2 terms from reaction 3 cancel out because we make equilibrium assumptions for reaction 3. So that's essentially the same as equation 5. Is it clear to everybody? Okay. So now after doing this, we have been able to express. So if you see the bottom thing here, the last line out here, we have been able to express our CES as a product of CE and CS divided by the Michaelis constant Km, right? So the Michaelis constant is still the same, it still retains the same form. Clear? Okay. Then what else? What else is left to do? Constraint equation. So these are the steps, so you should be able to, by now you should be completely thorough because we're at the end of this chapter. So this is the way to go. So we finished our equilibrium assumptions, we finished our quasi steady state assumption. The last thing left is the constraint, which is not an assumption, but it's a reality. It's something that really happens. So the constraint is going to have 4 species, as we discussed. So all the free enzyme and an enzyme in the 3 different forms, which is ES, EI and ESI, together should be CE naught, which is the total amount of enzyme present in the system to start with. Okay. So what you do is you keep this and then you substitute for each of those complexes. So CES can be substituted as CE times CS over Km. CEI could be substituted as CE times CI over KEI, and CESI could be substituted as CE times CS times CI over Km over KESI, right? So now we've been able to express all of these complexes in terms of the basic elements. Now the next step is, as I said, CE is also not something we really know, and we want to express everything in terms of CE naught. So we express everything CE in terms of CE naught as CE equals CE naught over this denominator, and then we can put it back into our last equation, which is which equation is that? The last one is the rate limiting step, the rate of product formation, right? Clear up to this point? Okay. Okay. So, yeah, in case you need more time to write things down, always let me know. So, the final thing that we are going to do is the rate of product formation, which is ddt of Cp, which equals K2 times CES, and K2 times CES is Ce times Cs over Km. Now, this Ce we can replace by what we just calculated in terms of Ce naught, and this is what you get, right. Now, yeah, so once you have written that, what I would like you to do is rearrange it in terms of the form, the Michaelis-Menten form, if it's possible. It may not be possible always, but maybe. So, this is a little quick thing I want you to do. The rate is given on the screen. What I want you to do is rearrange it in terms of the, so that it looks like a Michaelis-Menten form, or try to at least. Then, so what you essentially have to do is, you have to have a Cs in the numerator, and the denominator should have a constant plus Cs, right. So, you have to evaluate that constant and the other constants that are prefactors of the Cs in the numerator. So, yeah, if you are stuck, you can just look up in the screen, the answer is there. Okay. So, now we can write this as R max Cs over Km hat R tilde. So, I used hat for the last one. So, and this one I am using tilde. So, R max tilde Cs over Km tilde plus Cs. Okay. So, this is the Michaelis. The Michaelis-Menten form, essentially you have to do it like an R max Cs over Km plus Cs. That is the form you have to get to, right. So, your R max is now K2 Ce naught over this term, right, here, because see what happens is, this is the prefactor of Cs, okay, prefactor, postfactor, however you want to call it. So, this is comes with the Cs, but you want the Cs free, right, you do not want it with any other constant. So, you divide the numerator and denominator by this term 1 plus Ci over ESI, right. So, then you get your R max as K2 Ce naught plus 1 plus Ci over K ESI, and your Km tilde as old Km times 1 plus Ci over Ki, that comes from here, divided by 1 plus Ci over K ESI. Okay, fine. Now, can you tell me by looking at R max tilde and Km tilde, if these are going to be larger and smaller than your Km and R max? Smaller always, right? We cannot conclude about that's the right answer, yes. So, R max is, if you look up there, R max is smaller than always smaller, but we cannot make because why is R max always smaller? Because Ci is larger than 0 and KESI is larger than 0, so it's always smaller, but we cannot make such conclusive comments on Km tilde. The reason being, what is the reason?
We don't know, we cannot compare KI, ESI.
Yeah, so it depends on the relationship between KEI and KESI. So, depending on whichever is greater or smaller, you will have different kinds of relationships. Okay. So, so why is this useful? Why is this? Probably this is more useful a method if you want to control, regulate the enzyme inhibition. Of all the three methods that we have learned, this is probably the most useful, because you can control both the slope and the and the maximum rate. See, why, think from a realistic point of view. So, in most cases we want to reduce the maximum rate, right? That is something that we discussed, because we do not want excess product formation. We want product formation up to a certain range. So, that why, if you go back to some of the things that we discussed, is that the products are typically active within a certain range, because they might be triggering off some other biochemical pathway, some desired biochemical pathway within that range, and outside that range they might be triggering off other biochemical pathways, A. And B is that you don't want excess product formation, because essentially it's a waste of energy. So, you want to reduce your maximum reaction rate always, but your slope, which gives you the rate of initial product formation, how you start off and how you reach that asymptote, that is given by the slope. That is something that you want to regulate, and by regulate, I don't necessarily mean that you want to decrease it. That is something that you want in your hand. You should be able to increase it or decrease it. Okay. So, in one kind of inhibition, you essentially, so first kind of inhibition, the competitive one, we saw that you can change it, but you can change it only one way. And the second kind of inhibition that we saw, the uncompetitive, we found that you cannot even change it, because what turns out that the Km and the Rmax differ by the same ratio, and the slope is dependent on the ratio of these two, as a result of which there is no dependence on the of inhibition on the initial rate. Here you find that there is dependence of inhibition on the initial rate, and you can change it well. And by change it well, I mean that you can change it positively or negatively. They can decrease it or increase it. So, this is the most convenient form of inhibition, because of both reasons. It's the most potent and most flexible, because you can make the most amount of changes in this. The next thing I am going to show you is a comparison of the plots because I haven't showed you a plot for either competitive or uncompetitive or non-competitive. So, I am going to show you a comparison of the plots, but by now I think I have clarified most of the concepts. So, what the plot is going to catch is essentially that in uncompetitive, the initial rate of product formation is independent of the inhibitor concentration, right? The initial rate is independent of the inhibitor concentration. The reason being that the slope is a constant. It's independent of initial concentration, independent of initiator concentration. Sorry. Whereas in non-competitive, both the slope and the maximum rate could be changed by the inhibitor. Now, as you see over here, the constants for ESI and EI have been taken to be the same out here. Okay. Both have been taken to be the same, but if I varied it accordingly, I can change the slope the way I wanted. So, this here it isn't taken the same. As a result, you get one kind of inhibition. What you might want to do, go back home and do a quick calculation, is that as you change the Ki, so if your KESI is 10 times that of KEI, which way the slope will go, and if the other way it's like 1/10 of that. So, you do 3 different cases, equal, one is 10 times, again that one is 1/10 of the other. Then you will see, you'll have a sense for one particular inhibitor concentration, how you can bring it forward and backward, right? So, that's something that you might be able to do. So, this is about inhibition or enzyme regulation using inhibitors. Okay, this is all we wanted to do. The last thing that we are going to do is another kind of inhibition, but which is not initiated or influenced or dictated by inhibitors. It is a natural process, an intrinsic inhibition. So, when we talked about inhibition in the first one of the earlier lectures, we talked about intrinsic and extrinsic inhibitor. So, in extrinsic inhibitor, you can add the inhibitor from outside, say, and make these kind of inhibition happen. And in intrinsic inhibition, there are 2 possibilities. One is that the inhibitor is there inside the system itself and kind of inhibits a set of reactions. The other possibility is that the substrate itself inhibits the reaction. Okay, there could be possibilities where the product itself inhibits the reaction. Okay, some of you probably might know there are quite a few reactions where the product itself inhibits the reaction. So, if the product itself inhibits the reaction and you do not want inhibition, for example, what would you do? Very straightforward answer. What did you do? if the product is inhibiting the reaction and you do not want the inhibition to happen. Constantly take out the product, yes, that's the right answer, but see, if you have there's a problem. If you have a big reactor and you have a CSTR essentially, so and what happens if you have a big CSTR? What is large in a large CSTR? What would be large in a large CSTR? Yeah, volume large means what? The residence time, right? The residence time is large in a large CSTR, right? So if the residence time is large, and even if you are taking the product out at a certain rate, then still, because what does residence time signify? It signifies the amount of time, not the exact amount, but a representative amount of time that each of the species gets to spend in the reactor, right? That is the definition of residence time. So even if you are taking it out at a constant rate, say in a CSTR, what is the problem? The problem is the product gets to spend a fair amount of time in the reactor, right? As a result, it will still be inhibited. So yes, taking the product out continuously is a theoretically correct answer, but it's not a practically correct answer, because if you're using a CSTR, it has a certain residence time and you cannot do anything beyond it, right? So what would be the other mechanisms? One of the ways, of course, is to keep the volume same but increase the input-output rates, right? For a steady-state CSTR, to increase the input-output rate so that the residence time is decreased. That's one of the possibilities. But what could be other possibilities?
We can reduce the formation of rate of formation of product.
Then how will you reduce that?
By varying the flow rate.
No, flow rate we already said, that's a possibility, that you can increase the flow rate, as a result of which you can decrease the residence time. That's one possibility. What are other possibilities?
By reducing the RPM.
No, RPM, no, let's not get into mass transfer resistance at this point. Okay, the answer is this, that you instead of using one large reactor, replace it by several reactors. So if you have a reactor of say 10 hours residence time, replace it by 3 reactors or 4 reactors of 2.5 hours each. So the total residence time is still the same. Okay, and if you keep the total amount of the flow rate as the same, then you essentially divide up. So a 10-liter reactor, you divide up into 4 2.5 liter reactors, right? So as a result of which, say if your flow rate is 1 liter per hour or something, and your 10-liter reactor is there, so your residence time is 10 hours, right? So now if you split it up into 4 different reactors, your residence time is 2.5 hours each, and your reactor volume is 2.5 hours each. Okay. So what will happen is that you intermittently you can take out the product. Okay. So without changing the total residence time, you still keep the total residence time and the total reactor volume the same. But what happens is, as soon as the product comes out as a mixture of product and reactant and other things that come out of the first reactor, you take it out, you pass it through a membrane separator unit, take out the product and recycle back the rest of the thing into the next reactor, and then you keep doing this all the time, right? Is it clear? So as a result, you will intermittently take out the product. So this is one way you can stop inhibition from the product. But the problem is that life is a little more difficult when the substrate starts to inhibit. Okay, when the substrate starts to inhibit, and there is another kind of reaction, you probably know that, it's called autocatalytic reactions. Okay, so the autocatalytic reaction is what is autocatalytic reaction? It's just catalyst. Yeah, so essentially what we talked about just now is an auto-inhibitor reaction, where the product inhibits the reaction, and then you can have autocatalytic reactions where the product catalyzes the reaction. Okay, now just as auto-inhibitor reactions are bad and you do not want the product to inhibit the reaction, the autocatalytic reactions could be bad as well. Why do you think so?
Very fast.
Then what will happen?
Reaction rate will keep on increasing. Reactor can burst.
Yeah, right. That's a very good answer. So what happens is a phenomena called reactor runaway. Okay, there's a phenomena called reactor runaway, and these reactor runaways typically happen in autocatalytic reactions. Okay, one of the things that you do not know, I'll tell you in a few minutes, but you talked about exothermic. Forget about exothermic, and I'll come to that in a minute. See, simple non-isothermal reaction, for example, A plus B, A plus, let's say A plus B giving 2B. Okay, so that's an autocatalytic reaction. So okay. So here, for example, A is your reactant, B is your product, and this B itself goes and catalyzes. Okay, so this is an autocatalytic reaction. Okay, so so the thing is that this B is going and catalyzing, and so the more B you produce over here, the more the reaction is catalyzed. Okay, so what you're talking is about exothermic reactions. So the reactor can go through what is known as burst out completely. But even apart from that, the reaction rate goes out of control. Okay, the reaction rate will go out of control, because what will happen with time, more and more product is going to be formed, and the more and more product is formed, the more and more it reacts. But the way to stop that is to control your feeding of A. Okay, so control your feeding of A. So what you do is, you don't put in all the A at the start, you put in slowly. Okay, and the rate at which, so your A is now going to be the limiting reactant. A is going to be your limiting reactant, and the more you limit the amount of A that is formed, that is there in the system, the more the reaction is limited. Okay, so so this is good, but what I'm going to talk about now is what he said, and that's a more interesting phenomena. Let's say 2B, or you can have it differently also. This is a more famous form actually. This is what I wrote on the top is a more famous form. This is a Gray-Scott model. This is known as the Gray-Scott model. So, and a huge amount of theoretical and experimental studies have been done on these autocatalytic systems. And I'll come to a minute why these studies actually had been done in these autocatalytic systems. So, you can have a system like this, or so let's call this isothermal, or you can have a system as A going to be exothermic. Okay. So if I have A plus B giving 2B, what would be the reaction rate? Yeah, or if you have A plus 2B giving 3B, then the reaction rate R equals minus Ca Cb square, right? Fine. Now let me ask you this: A plus A just giving B exothermic, what is my reaction rate? R equals minus K into, so let's call this K into Ca. That's it. First order, yeah, but exothermic, what is the reaction rate? K naught into exponential minus right. And this is probably, I'm sure, this is something you know, but there's something I'm going to tell you that you don't know. So this reaction is autocatalytic. Do you know this? Have you learned this before, that this is autocatalytic? This is autocatalytic, right? Think about it for half a minute, you'll see what I'm trying to say. You see why it's autocatalytic? Temperature is a catalyst here. Catalyst equals temperature. Okay. So here catalyst equals temperature. You see what I'm saying? Because this is exothermic, so heat is going to be generated. Okay. The more the heat is generated, the more the temperature is raised. More the temperature is raised, more this term goes up. Why? Because its temperature is in denominator and there's a negative sign. Okay. So essentially it's a positive effect. So temperature goes up, this term goes up, right? So the more this term goes up, the more the reaction rate goes up. Clear? And more reaction would happen, and that would raise the temperature even more, right? And this would go on. Now this is, all of you are chemical engineers, most of you are going to go into industries to work, and what you will see is most of the reactions that happen in the industries are of this type. Okay, not many reactions are endothermic, most reactions are actually exothermic. So exothermic reactions, this is the simplest case we assume, first order. If you take second order and so on, third order is hard to come across, but second order, if you say, it gets more complicated. So the simplest case we're looking at, simplest exothermic reaction, and that's autocatalytic. So that's a huge trouble. Okay, that's a huge trouble in industries. And so I think you were telling me that in your company you used to have accidents very often. So no wonder you'd have so accidents is a possibility. And that is why it's very important to be able to control these reactions, either by inhibiting them or by coming up with other means, for example, feeding it in a different way, or for what happens is that now let's come to the concept of reactor runaway. So one of the things that you can continue to do is cool it either by jacketed cooling or by a kind of cooling where you couple up an exothermic and endothermic reaction, so that the heat produced by exothermic reaction is quickly taken up by the endothermic reaction. So these are different strategies that you come up with. Now, what is a reactor runaway? Okay, reactor runaway is not necessarily the fact that this would get very hot. This because of the reaction, the heat generated. This is the reaction rate, and because of the heat generated, the reactor becomes very hot and bursts. No, that's not possible, because as engineers we design these reactors properly enough so that they would not burst so easily, so that there is no reactor runaway. Reactor runaway is essentially that if you have a reactor like this, and these are large reactors, okay, and you are mixing them, okay, at several points, let's say, and here is your reaction happening A, everywhere it's happening. Now what happens is these reactors are real reactors, and there are different kinds of perturbations, disturbances. So so there could be disturbances on the floor, there could be disturbances in the jacket, on the side, there could be different disturbances in different places. So for example, if you are having a jacketed cooling, the cooling in one side may be different from the cooling in other side. These are normal things that happen in a chemical reaction, and these are things that you cannot control. You can control the amount of coolant that flows in, you can control the amount of the reactant that comes in, but you cannot control these things which are out of your control, essentially. For example, influences or perturbations or changes or fluctuations in the coolant rate and so on. So as a result, what happens is that the temperature is not uniform. A lot of effort is put in to make these temperatures uniform, put in as many stirrers as you want, but the temperatures are not uniform in the reactor. That's a reality one has to live with. So what happens when a temperature is not uniform in the reactor? Hotspots would generate, but essentially in terms of the reaction, what would happen? If I look at this reaction A plus B, what happens? You think about in the terms of the reaction rate. So if temperature is more at a certain place, and these reactions are autocatalytic where the catalyst is temperature. So if temperature is higher in one particular end of the reactor than the other end, then what would happen is that the reaction would be higher in that particular end as compared to the other end. So what will happen is that so what will happen is this A going to be over here and A going to be over here as well. But if the temperature T here is T1 and this is T2 and T1 is greater than T2, then this will the reaction rate will here go up, okay, and so more heat will be generated over here, and that heat will catalyze even more reaction. So what will happen is the hot will get hotter. So this is like the rich getting richer. So a very capitalistic model works inside the inside a chemical reactor, so to say. And this is a very normal case. I'm taking a very simple case of an exothermic first order reaction. Remember, this is not a very complicated reaction, no network, nothing. The very simple case of first order exothermic reaction which you come across all the time, and this is what happens. So those things that are, so this hot areas that are generated are called hotspots. Okay. So these are called hotspots. So hotspots are essentially when one part of the reactor starts to get hotter and hotter and hotter, and what will happen? What will coincide with hotspots? What if there is a hotspot in one part of the reactor? What will happen? But in other parts of the reactor, the reaction rate might go down. You know, there could be cold spots. The reason is that the total amount of energy that is typically given to the reactor is more or less a constant. So there is a possibility that the other regions might cool down. There is a possibility. I'm not saying that it will necessarily happen, but there's a possibility. So when these hotspots blow up, that is, you have hotspots in different parts, okay, and the temperature, so few hotspots in different parts of the reactor, and temperatures in these hotspots become much greater. So if the average temperature elsewhere is T2 and T1 is the temperature in the hotspot, then if T1 is much greater than T2, when this happens, the reactor blows up. So when a reactor blows up, it's not that the entire reactor blows up, it's not that the temperature in the whole reactor is very high, it's that certain parts of the reactor become extremely hot and cannot be handled, and it blows up, and that is called reactor runaway. Okay, that is this phenomenon is called reactor runaway. So so why, you know, if I talk about let me go a little bit more into the detail at this point of time. So if I take a reaction like this, okay, minus k, say r equals minus k naught Ca exponential minus E over RT. So I take a reaction rate like this. Now we thought about it practically, and we looked at the practical part of it, but you know, one of the things we want to do is bring down the theory and practical things together. So if you look at this equation mathematically now, what is there in this equation? You know, I want you to think from a completely different angle now. If you look at this equation mathematically, what is there in this equation that can make such a thing happen? No, not rate constant. Yeah, what is there about the exponential part? Of course, the fact that it goes up and so on, but mathematically, I want you to think more mathematically now. Fine, but if I had given, you know, if I had just given any other increase form of increase, what is so curious about this particular form? What is so interesting about this?
Each of the E, R, and T are positive, and we have a negative sign of T. So if any of them are less temperature.
Okay, I'll give you a simpler example. Okay, I'll give you a simpler example. This A plus 2B giving 3B. Okay, let's look at this. Isothermal. So that also gives the similar kind of thing, right? That's also why is it? Because this is also autocatalytic, this is also autocatalytic. So this is a little more complicated. So let's look at the simpler form. So here Ra equals minus K CaCV square. Okay. So Ca is same here. Let's call this K naught. K naught is same here. So if you compare this with this part with this part, okay, what is interesting? What is important about that? This and this. You have to get this. Mathematically, let's not think about the but yeah, what is the basic thing? I want you to utter that word. What is the basic thing? There's a nonlinear dependence, that's the thing. So this catalyst, whatever, be the catalyst could be B or the catalyst could be temperature. There's a nonlinear dependence on this catalyst, and that is what is allowing such a thing to happen. Okay, conceptually, let's maybe at some other time, next class, I'll talk about it a little more. But conceptually, let's try and understand what is happening. So coming back to this picture, so the temperature is T1 over here, and the temperature is T2 over here. This is supposed to be a completely thoroughly mixed reactor, okay, continuous stirred tank reactor. You know one thing, that in the continuous stirred tank reactor, only one temperature is allowed. But here what is happening, maybe two or more than two temperatures are present in the same reactor. Does it make sense to you? So what is happening? What is this phenomena called? Do you know this? So at same point of time, okay, in different points in space, two or more different temperatures coexist, and that is allowed by this form of these equations, this equation and that equation. Okay. So at the same point in time and two different points in space, two different temperatures coexist. Or if you're talking about A plus 2B giving 3B, two different values of B coexist, two different amounts coexist, but these are supposed to be continuously stirred, tanked, completely mixed reactors. So despite all the mixing, so this is allowed because of the form of the equations, and this is multiplicity. Okay. So essentially there is multiplicity. So these equations, these forms allow that kind of thing. So maybe next class I'll talk a little bit about bifurcation and multiplicity, because there are other things that will show also which have to deal with multiplicity. But because of the basic thing that multiplicity is allowed by these equations, okay. So at same point of time there could be two temperatures in space, or two values of a certain constant substrate or a certain product in space within a continuously stirred tank reactor. That is multiplicity, and because multiplicity is allowed, that this is allowed to happen, right? Otherwise, unless multiplicity is not allowed, then temperature in one spot cannot go up while the temperature in another spot remains the same. Is it clear? But that see that is from a physical point of view, you're thinking it makes sense, but it has to be supported and allowed by your theoretical framework, your theoretical equations that you have, and that is supported and allowed by this particular thing. So this is, I think, something very important I wanted to discuss today. It's not completely directly related to what we are doing, but as chemical engineers you should know that a very simple equation like a first order exothermic reaction, which is something that you handle all the time and you will handle all the time for the rest of your life, is autocatalytic, and these are some of the very complex phenomena that it can lead to, and that is why it has been studied in such great detail over the last say 40 years. It has been studied in great detail, lots of work has been done on it. So a little bit we'll come across in our next lecture, which has to deal with bifurcation and multiplicity, and I'll give you some sense of it. So next class we'll finish the substrate inhibition and the rest of the chapter. So this week we'll finish that. So thank you for being here, and so we'll continue with the substrate inhibition and the rest in the next lecture. Thanks.